So to start as a motivation, let me say that mechanical structures such beams and flats are a central part of our life today, almost everywhere. So as you can see in the picture, many structures may contain beams such that automobile frames, aircraft components, machine frames, etc. So in order to understand the deformation and the vibration of a beam or flat, there is theories that can describe the transvibration of a beam. So we note here there exists two major theories, the Euler-Bernoulli theory and the Timoshenko theory. Well, the Euler-Bernoulli theory assumes that the cross-section is always perpendicular to the bending line, and also it neglects the effect of shear deformation. So here, as you can see in the picture, we have a fixed beam, such that means mathematically speaking, we have a directly boundary condition. And when we exert a force, the beam will deform. We have a small deformation. So for the Timoshenko theory, it does not assume that the cross-section is always perpendicular, while it takes into account other value of the rotation angle. So it allows rotation of the cross-section with respect to the bending line. And also it includes the effect of a shear deformation. To be more precise, I will present by this picture the deformation of a beam. So which is in red, this is the Euler-Bernoulli approach, and which is in blue, it is the Timoshenko approach of the deformation of the beam. So mathematically speaking, the Timoshenko approach described by the following couplet system. As you can see here, we have a system composed by two equations, PDE, such that phi here represents the displacement vector and psi represents the rotation angle. Also, we have rho, k, e, and a are a physical parameter, and it is assumed to be a positive constant. Also, L here represents the length of the beam, and of course, the displacement vector and rotation angle depend on the time and space variable. Of course, the vibration of a beam are undesirable. So in order to reduce the harmful vibration, several control mechanisms has been designed. And let me give you a little, some result already obtained. In the linear case, that means if we assume that we have this system subjected with two damping linear term, that means we have a linear term on the first equation and the linear term on the second equation. In that case, the system is exponentially stable. That means the energy goes very fast to zero when time goes to infinity. But when we only assume that we have only imposing a linear damping on the second equation, the energy which have this expression goes exponentially to zero when time goes to infinity, but with respect to this relation. That means if and only if we have V1 equal to V2, such that V1 and V2 represent the wave speeds. Those results has been obtained by Sofiane Abdelaziz and also Rivera and Rack. Now, if you assume that we have this system, that means the conservative system without any linear or non-linear term, and we add to the second equation a non-linear term of the form a function that depends only on x, and also we can assume that we have a more general non-linear damping. That means if we here replace a of x by a function that depends together on t and x, and we assume that we have either the Dirichlet boundary condition or the Newman boundary condition, and of course we need to complete the system by the condition, the initial data, and of course we need to assume that the damping, non-linear damping term satisfy some assumptions, which are giving as follow. With respecting to those assumptions, we have that the energy satisfies two assumptions. The upper energy estimate, which is obtained under the condition that we have equality between the V1 and V2, and also we have a lower energy estimate that is given by this inequality. So as you can see here, we have an explicit expression of the upper energy estimate, but those two estimates have not the same. So upper and lower energy estimate give prove that the energy goes to zero when time goes to infinity, but they don't have the same rate of convergence. So we cannot obtain the optimality, but it is important. It is an important step because it gives us more precise characterization of the decay rate of the energy. And those results was obtained by Fatiha Al-Labou in 2011. So our goal was to study more general Timoshenko systems that describe the thermoelasticity phenomena and to investigate the optimality of the decay rate of the energy using this method, using upper and lower energy estimate. To do that, well, to understand the thermoelasticity, we have two laws, the Fourier law and the Continuum law. For the Fourier law, we have that the relation between the heat flow and the temperature is given by this equation. So the heat flow is proportional to the temperature, such that K here represent is the conductivity of the material. Sorry. This relation together with the energy equation of the heat conduction give us a parabolic type equation. So we have infinite wave speed. To overcome this paradox and to have a more general description of the thermoelasticity phenomena, we have the Continuum law, because the Continuum law gives this relation between the heat flow and the temperature, and we have an parabolic differential equation. So it performs finite wave speed because it gives us a parabolic equation. So we will investigate, so we will consider a one-dimensional Timoshenko model with thermoelasticity with a second sound. We will investigate the existence and uniqueness of the solution, study the strong stability of the energy, and also try obtain the expression of the lower estimate of the energy. So before that, let me cite some results, already obtained results. So for this system, which is a one-dimensional system with thermoelasticity with a second sound, as you can see, we have 4 equations, and the last equation is represent the Continuum law. For this system, even without adding any linear damping term, this system is no more conservative. So no more conservative, and the energy does not goes to zero when time goes to infinity as exponential function. So under the condition that V1 equal to V2, we don't really, the Continuum law made the system no exponential stable. So we need to introduce a new stability number, which is given by key, and the exponential stability is obtained if and only if we have key equal to 0. This result was obtained by Fernandez and Rivera. Our objective was to establish the lower energy estimate for a nonlinear damping term, a Timoshenko system with thermoelasticity, and use the lower and the upper energy estimate that already depend on the new stability number key, and also investigate the optimality result for an explicit example. In order to do that, We consider the following non-linear damped system. So as you can see here, we have the second equation imposed with a non-linear term of the form A of X, G of Ct. The initial data are giving as follow, and we assume that we have a directly boundary condition. That means we assume that the beam is a fixed beam. Of course, we have to put some assumption on the non-linear term in order to prove that the energy is a dissipative function. Remark here, as you can see, that we measure the function g by second function, which is C0, in order to capture the behavior of a damping close to 0. We have this function, which is h of x that depend on the function g. This function is important because it will give us an explicit expression of the assumption estimate. Also, we have this assumption, which is HS, which will be used later to prove the strong stability of the energy. The first result is the existence and uniqueness of the solution. Under the assumptions, the later assumption on the nonlinear term, we have the strong solution that depend. We know that the regularity of the solution depends on the regularity of the initial data. So when the initial data is in the space H, which is a Sobolev space, and all, we have a strong solution. And for this one, we have a weak solution. The energy is taking into account the temperature and the heat flow, of course, and we have that the energy satisfies the dissipation relation, giving us follow. And A plus B is generated a continuous semi-group. Now, A and B are the operator defined as follow. Idea of the proof, we need, in order to prove the existence and uniqueness of the solution, we need, first of all, write the system of this form and prove that the operator A is a maximum monotone operator and B is a nonlinear operator Lipschitz, in order to apply the Ilushida theory and prove the existence and uniqueness of the solution. Now the challenge was if we obtain a new equilibrium state of the energy. That means the energy does not go to 0 one time goes to infinity, but it go to another constant. How can we prove the strong stability, and how can we characterize the decay rate of the energy? Well, to overcome these challenges, we used the strong convergence and the well-known strong stabilization result due to the performance. And also to obtain the decay rate of the energy and characterize the decay rate of the energy, we use a no expression of the energy, epsilon t. Before I give you the result, we need to remind the definition of W limit, which is given by as follow, and also we use the Lassal inversion principle. So those two, the definition and proposition are useful to obtain the next result, which is as follow. So a new equilibrium state. The energy will not go to 0, but it goes to another constant given by E infinity. So we prove the strong stability of the energy, the new energy, epsilon of t, goes to 0 when time goes to infinity. Sketch of the proof, we adopt and apply the deformous strong stability technique based on Lassal inverse principle. That means we will assume that X here is the space, the H space, which is Banach space. And also we will use the dissipation property of the first order energy, giving as follow. We prove that the orbit is relatively compact in H. And also we assume that the function, the Lyapunov function that we will use it is the energy. Also, we will use the assumption H of C in order to prove that the energy have a strong stability. Now, to prove the lower energy estimate, we need to put a new assumption, a supplementary assumption on the function g. That means here h is this function, and also we have a gamma of x, which is the function represented by this expression. This function will give us a classification of the damping. And also we need to use the key comparison lemma, which is a very important lemma that will give us and made us prove the lower energy estimate. And this is the result. We prove that the energy, the new energy, is satisfying this lower energy estimate. So it depends on h, on the function h. And also the important result is that the optimality of this, the optimality is proved for an explicit example. That means for g of 0 equal to this function, we have the energy satisfying logarithmic decay rate stability, logarithmic stability, which is optimal. As you can see here, we have the upper and the lower energy estimate have the same decay rate. Sketch of the proof. So I just give the technical that we use it. So we need first of all to measure the velocity here, taking into account the regularity of the solution. Also use the assumption H1 and the dissipation relation in order to estimate the derivation of the energy, and then apply the key lemma in order to prove the lower estimate. Those are some other examples. So for g of s equal to s power p, we have a polynomial decay rate of the energy, but we did not prove the optimality because we don't have the same rate of convergence. Here also we have between exponential and logarithmic stability. Later on, we moved to study the behavior of the energy associated to the solution of a new system, which is midline Timoshenko model. Why? Because in high dimension, we don't see the transverse vibration of a beam, but we study the behavior of a plate. So here we don't have only one rotation angle, but we have two rotation angle and a displacement vector. That's why we have a system composed by three equations given as follows. Of course, here also we have ρ1, ρ2, and d mu are physical parameter, and it is assumed to be a positive constant. A little overview about the results obtained. So this system with a linear damping acting only on the first equation, that means if we add a linear term to the first equation, to the displacement vector, and also if we add two linear damping term to the second and the third equation, we prove that the exponential stability is obtained if and only if we have V1 square equal to V2 square. So even for two-dimensional system, the stability, the decay rate of the energy, it depends on a relation between the coefficient of the system. We assume that we have the decay, the nonlinear term Q1 of Ct here and Q2 of Vt. So we have two nonlinear term imposed on the two equations. Our objective was how is it possible to stabilize the system and find sufficient dissipation to produce this decay rate, and drive a general explicit decay rate of the energy when system is non-linearly damped. We consider the boundary condition, Dirichlet boundary condition, and the initial data giving as follow. Here, we assumed that the domain is a rectangle, so we have L1 and L2. The boundary is giving as follows. The energy of the system have this expression and the nonlinear term satisfying this assumption. The dissipation relation is obtained. Of course, it depends on the nonlinear on the two nonlinear damping. The general result is as follows. So under the condition that V1 square is equal to V2 square, and we assume that this function have a limit minus than 1, then the energy satisfies this expression, this general and explicit assumption. Sketch of the proof. So here the proof is a little bit not complicated, but it contains many technical arguments. We use the multiplier technical and weight function in order to prove this inequality. Then we assume, as you can see here, we have this term that it need to be equal to 0. So we assume that V1 square is equal to V2 square. And of course, we need to introduce a suitable partition of the domain omega. And we apply the Johnson inequality and the assumption on the nonlinear damping in order to obtain this inequality, and use the classification of the function gamma to prove that the energy satisfies the lower energy estimate. Now, for the numerical approximation, we were looking for trying to obtain a confirmation of the result that already obtained in the theoretical analysis. So we consider the one undamped Timoshenko system in a continuous case. That means we assume that we have this conservative system, and later on we put a non-linear term to the second equation in order to see the behavior of the energy. And to do that, we need to have do the total, the full discretization of the system. So we used the finite element method to obtain the space discretization, and the finite differential method to obtain the time discretization. Our system will be written as follows. So the matrix formulation of the semi-discrete problem is given as follows, such that M is a mass matrix, and K is a rigidity matrix, and S is a skew symmetric matrix. In order to do the complete discretization and the time discretization, we used an explicit schema giving as follow. And of course, we need to have the stability of the discrete problem. That means we need to respect the CFL condition between the space, the step of space and step of time is minus than 1. The energy, the expression of the energy is given as follow, and the first step was to prove that we have the conservation property of the energy, because the system is a conservative without any damped term. We assume that we have the initial data, polynomial 1, satisfying the boundary condition. So here we have the picture that represents the initial data phi0 and C0. As you can see here, the solution is undamped. So when time is equal to 500, we have, and for the length of the beam equal to 1, with respect to the CFL condition, we have this representation of the solution, undamped solution. Here, the system is conservative, so the difference between the energy is equal to 0 when, with respect to the CFL condition. Now, if we put a linear term to the second equation, we prove that the difference of the energy, the derivation of the energy, the approximation of the derivation of the energy is negative, have a negative form. So we have the dissipation of the discrete energy. And as you can see here, the solution is damped. So here we have a maximum of 0.2, and here we have a maximum that minus than 0.2, and here we have a maximum that minus even 0.1. For each time we change the coefficient of the damping term. Here is the behavior of the energy. So we can see that the energy goes to 0, one time goes to infinity, with a different value of the coefficient of the damping. And here for time equal to 5,000. So the energy will go very fast to 0 when time goes to infinity. To prove the exponential stability, we need to have the figure of logarithm of the energy in function of the time, and that proves that we have a line. So that proves that the energy is exponential stable. And those results gives us 3 publications. The first one is with Professor Ahmed Bshatniya and Makram Hamouda, and also with Abdelaziz Sofiane. And the second one was with me and my Professor Ahmed Bshatniya. And the final one is with me and Professor Ahmed Bshatniya and Professor Makram Hamouda. And thank you for your attention.
Thank you very much for your very interesting talk. So I am opening discussion. So there are some questions, remarks, so please go on. Yeah, Pavel, please.
Okay, hello, good afternoon. Am I allowed to ask the first question? Yeah, so, hello, Sabrine, please give my best regards to Ahmed Bshatniya. And so my question is the following. Can you go back to page 15, please?
Page 15. Okay.
15.
15.
13.
Ah, okay.
Yes.
Okay.
Yeah.
Okay.
No, this is 13.
13, 14, 15.
Ah, okay. 15. Okay.
15.
Now.
Yes, here it is. So normally in thermoelasticity, it is assumed that the mechanical dissipation is transformed completely into heat, and that the full energy is conserved. But here it seems that you neglect the contribution of the mechanical dissipation to the energy balance. And so it seems that your energy is decaying to something, possibly to 0. So the temperature is decreasing in principle in your process. So what is happening with the dissipated energy in reality in your model?
What is, I'm sorry, what is?
What is happening with the total energy? Because if the mechanical energy is not transformed into heat, which is obviously not the case. And so what is happening with the dissipated energy instead?
Well, here, if I understand the question, here you speak about the system without any damping term.
No. The damping is okay, but
Okay.
the dissipated energy normally is assumed to contribute to the energy balance, but you don't really have a perfect coupling between the energy balance and the mechanical dissipation. So in your system, the energy is disappearing somewhere. And so my question is, where does the energy disappear?
Okay. Well, what I understand it is when we have the energy, so the energy is a decreasing function, it normally goes to zero, one time goes to infinity, because it needs to look for a stable state.
No, this I understand, but the energy decays to zero means that it disappears somewhere. Normally, in physical systems, the energy should be transformed completely into heat. And so my question is, what is the physical justification of the model?
Okay, I understand. So here, I don't really. So we have a mechanical energy, and we have the time, the temperature, and we have the heat flow. So the energy will dissipate, and I don't know.
Okay, I don't insist.
I don't know. Only what I know that it is a reversible system. That means it needs to come back to a stable state. So here we have the temperature and we have the heat flow. So the energy need to be divided on all the value. I don't know.
Okay.
I really don't know. I did not investigate this question. Sorry.
Okay, thank you very much.
Okay, thank you.
Okay.
But it is very interesting for.
Please go ahead, yeah.
Yes, it is very interesting to see where the energy it go when it does not be temperature. So here I don't know.
Okay, thank you.
Okay, so
just if I can continue this somehow observation, there is also a problem with the adiabatic heat. That the delta term in the mechanical part, this is some sort of thermal expansion, and then it may go to cooling, and also this is missing. Simply, this is the system is not thermodynamically consistent, so the Pavel has complete right, of course.
Mm-hmm.
Okay, thank you.
Okay.
Well.
Yeah, Tomasz, yes, some.
No, it was just a mistake.
Okay. Yeah, good. So, other questions, remarks? So it seems to be not the case. So, Sabrine, thank you very much for your presentation, and see you soon in Prague. In May, we somehow agree, if I remember well.
Yes, exactly.
Yeah, okay. So very good. So next week we will do something like mixture, which means that it will be not only online, but it will be in person. So next week we will really meet in Karlín, and talk will be done by Václav Mancha. It will be about some fluid. So we will see exactly if it will be fluid structure or just fluid itself. We will see. Okay, so thank you very much, and see you soon on next Monday. So bye-bye.
Thank you so much.
Bye.
Thank you. Thank you.